Well, good morning. Hope it's a blessed morning for you today. Our bell ringer is a binary to decimal conversion problem. What is the decimal equivalent of 10101010 from binary to decimal? Remember how to set this up. You want those 8 numbers lined up from the far right side of the number all the way to the left. Starting with the first digit, you've got 1. And then times 2 is 2, then times 2 is 4, times 2 is 8, 16, 32, 64, and 128. If there's a 1 below that number, you add that number. So there's a 1 by the 128. So we're going to add that. I'm going to put that into my calculator as we go. 128 plus, there's no 1 by 64, so we don't add that. But there is 1 by 32, so we're going to add 32. No 16, but an 8. So I add that 8. No 4, but a 2. So I add that 2. And there's no 1. So I'm going to hit enter. And our answer is 170. And let's see what our answer is. And sure as pudding top pie, yeah, it is 170. Let's talk about some good things. All right. Well, number 1 is Friday. Oh, number 2, it's Friday. There's nothing better than that. Friday means the end of the work week, end of the school days for you for the week. Nothing good times on the weekend, so let's go enjoy it. And another good thing, today's my birthday, so I hope you enjoyed as much as I plan to. All right, so decimal to binary conversion, and as this meme says, you're going to learn today. You've probably never done this before, so we're going to do what we can. You have a decimal number, how do you translate it or convert it into binary numbers? All right, the process to translate decimal to binary requires more calculation than binary to decimal. That's because most of us have 10 fingers to count with, and if we only had 2 arms and no fingers, we'd probably count using the binary numbering system. When we learn to divide, some integers do not evenly divide into other larger integers. So before introducing the decimal point, we learned to use remainders. So to complete the base translation, decimal to binary in this case, using those remainders called the modulo is the key. The use of the modulo to determine base translation is called modular mathematics. So in modular mathematics, we are only interested in the remainder or the modulo. If we have integer a divided by integer b, we're going to get a quotient, an integer, and a remainder r that's an integer. A is the dividend, b is the divisor, q is the quotient, and r is the remainder or modulo. When we divide 2 integers, we will always have an equation that also looks like this. A modulo b equals r. You can see that's how it's said there. In this example, b is referred to as the modulus. What we're talking about is instead of a divisor, it's a modulus. We're trying to find out what the modulo is. And that's the remainder after a number is divided into another number. We have nothing but integers in this equation. Say we spend 12 hours climbing a mountain range. This is an example of decimal to binary conversion. And 10 hours descending it. If we left at 5 a.m., what time of day did we return? So the solution is if we left at 5 a.m. and spent 12 hours climbing and 10 hours descending, we spent a total of 22 hours on the mountain. So if we add 22 to 5 a.m., we total 27 hours. Actually, it's not really 27 hours, it's 27. It can't be 27 o'clock, so we have to use the modulo or modulus 12. Because there's only 12 hours in a portion of the day. It only goes up to 12 o'clock. So we use 12 mod set, or set 27 mod 12 to find the modulo. We divide 27 by 12, which gives us 2, remainder 3. We want the modulo, and since we want the modulo or the remainder, the answer is 3, or 3 a.m. on the next day. This works because after every 12 hours, the hours are modular, which means they just start over. That's why it works. All right, from decimal to binary, we replace 12 in example 1 with a 2. Finding binary equivalent of the number is a series of modular mathematics problems. Time-consuming, but not difficult. Find the binary equivalent to 23,563. We divide the number by 2, keeping both the quotient and the remainder in a series. Keep the integer answer and the remainder handy to continue the process until the dividend is either 1 or 0. We then place all the remainders in order from the largest divisor to the 1 or 0 divisor, too small to divide by 2, to create the binary number. So 23,563 is divided by 2 is 11,781, remainder 1. Place remainders in backwards order to find the binary equivalent. We do this all the way through all the numbers. Notice we take this right here, and we're going to make it into a another equation, whatever is that. What do we call it? The quotient. After you make the division sign, you have the divisor and the dividend, and the dividend divided by the divisor, and you get a quotient. And then you get the modulo, or the remainder here. And you're going to use that quotient and divide it by 2 again and do that process all over again. Now we'll put them in backwards orders from here to here to give us our binary number, 10111, 000001011. That is our binary equivalent to 23,563 in decimal form. Now, while we can see the number is not an octet or 8-digit binary number, we now know how to translate decimal to binary. It takes more math, but it is simple work that can be calculated quickly. There are many other number bases, but most are not used. In computing, you may hear about octal and hexadecimal numbering, which is simply base 8 and base 16 number. Each are easily converted from binary and are often used. Don't know why that's still there, but that's okay. We'll continue. All right, what is the binary equivalent of the number 255? 255 divided by 2 is 127 with the remainder 1. 127 divided by 2 is 63, remainder 1. 63 divided by 2 is 31, remainder 1. And so on all the way down. Notice that the binary equivalent is 11111111. That is the 8-digit binary digit, or let me rephrase that. The 8-digit binary equivalent of 99,999,999, except it's just 11111111. That's it. So another way to do this is to use the dividend to help you create the binary number. So you take the number, divide in half, and ignore the remainder. Do this until you reach 1 or 0. Then simply write a 1 below odd numbers and a 0 below even numbers. It's another process to do it. You know that on an odd number, when divided by 2, has a remainder 1. An even number, when divided by 2, has no remainder because it divides evenly into that number. So that's another process to do it. You can check your answer, add all those numbers together, and you'll get 255. All right, let's do this on another example. Take the number, divide it in half, and ignore the remainder. Do this until you reach 1 or 0. Then simply write a 1 below odd numbers and 0 below even numbers. This is an example. The number 135. Notice I'm going backwards. This way, I'm going to start at 135 divided by 2. I get 67. 67 divided by 2 is 33. Then I get 16, 8, 4, 2, and 1. Pretty cool. All right, so that's our answer. We'll check our answer. What you do is you just set it up and do a binary to decimal translation or binary to decimal conversion to check your answer. That's all you're doing. Okay, we'll launch with this. I kind of think it's funny. Finds out his IQ is 100 in binary. There you go. This kid gets butchered in memes all the time. But you know what? Still kind of funny. All right, so there is an assignment in the Google Classroom if you haven't already done it because it's been there for a couple days. Please go to it, take care of that, and I'll see you on the next video. In the meantime, be blessed and be a blessing.